Let's go ahead and get started. Hi everyone, this is Ashley Childress with the Statistics Division of ASQ. I would like to welcome you and thank you for joining us today. Our speaker today is Willis Jensen. Willis is the Global Statistics Team Leader at W.L. Gore & Associates, where he leads a team of statisticians which provides statistical support and training across the globe. He has been at Gore for nearly 10 years and holds degrees in statistics from Brigham Young University and a PhD in statistics from Virginia Tech. He is an associate editor of Technometrics, the book's review editor for Journal of Quality Technology, and a member of the editorial boards of Quality Engineering and Quality and Reliability Engineering International. His research interests include all aspects of industrial statistics with a focus on applications to real problems. The title of the webinar Willis will present today is Confirmation Runs and Design of Experiments. All phones and microphones other than the presenters have been muted, so if you have any questions or comments during the webinar, please use the questions interface in the GoToWebinar control panel. I'll hold these questions for the end of the presentation, at which time Willis will answer those for us if there is time. So at this time, I'm going to hand things over to Willis, who's going to start us off with some audience questions. As the questions appear on your screen, please select your response. Willis?
So thank you, Ashley. I'm grateful for the opportunity to have to share some information here around confirmation runs with design of experiments. This is based on some work that I've been doing over the past couple of years while at W.L. Gore, and I'm just excited to have the opportunity to share some things. But before I get into the presentation, I really wanted to get some initial information about our audience there. We do have, it looks like about 100 people or so who are attending this webinar, so I'd like to get some information. So Ashley has kind of set up some poll questions for you. So if you will go ahead and answer those questions as we walk through them, and we'll be able to see the results in real time. And I'll be able to use this information in tailoring just a little bit the material that we talked about today. So the first question there is your affiliation. So if you'll go ahead and do that, I'll give everyone a moment to answer that question if you haven't already. All right, so based on the results here, looks like the vast majority of you from industry. That's good to know. The focus that we're going to be talking about today will definitely be from an industry, a practical focus, an applied focus, so hopefully that will be valuable for those who are coming from industry. So, good. So the next question is talking just about these webinars. So this is sponsored by the ASQ Statistics Division. So the question is whether or not you have previously attended a webinar by the ASQ Statistics Division previously. All right, so it looks like some of you, a large percentage of you have attended a seminar previously, so the 40%, and then a large percentage have not. So for those who have not previously, on the ASQ Statistics Division website, they will share future webinar topics and things like that that will be similar to the topic that you're hearing today. So I would encourage you to or if you're not a member of the ASQ Statistics Division, to be a member of the ASQ Statistics Division so that you can be notified when future webinars come in the future. So now let's get into a little more around the topics. When we talk about confirmation runs for experiments, I'd like to know whether or not you've actually performed confirmation runs, or whether maybe you're in more of a consulting role. So maybe you haven't actually done them, but maybe you've recommended confirmation run to someone else who is actually doing the experiment. So they'll just answer true or false. Okay, looks like a good percentage who have done that. And this is interesting to me because when you look at the literature, and this is where I really started when I was looking at the literature to try to see whether recommendations were in the literature, it was almost always consistently recommending that confirmation runs were something that should be done as part of any experiment, that was the best practice. But one of the things that I found is there wasn't really much guidance on how much to do, and this is what I'm going to share with you today is the result of my investigations of trying to establish some guidance and ideas around how many confirmation runs to do and the value in doing confirmation runs. So I'm hoping by the end of this hour that for those 42% who have said performed, or have not performed, or not recommended, that in the future that 42% will become a much smaller percentage. Hopefully I can convince you or show the value in doing confirmation. And one of the things that we're going to be talking about today are different types of intervals and ways to assess confirmation runs, and how do I know whether or not a confirmation is successful. So I'd like to understand if you know the difference between a confidence interval and a prediction interval. Okay, that's good. So when we talk about, just as a brief introduction, confidence intervals, when we talk about a confidence statement around a mean value, and a prediction interval when we talk about a confidence statement around individual values. So for example, in a confidence interval, you could say something like 99% confidence that the true mean value is between 10 and 15, which is a different statement than if you say something like I'm 99% confident that the next future individual value will be between 8 and 17. So in general, a prediction interval is wider. It implies some sort of prediction around individual values oftentimes. Now there are different kinds of prediction intervals. There are different kinds of confidence intervals, but typically the confidence interval is going to be around a parameter of interest, whereas a prediction interval is more around a future quantity or an individual, typically. And as I get into this a little later, I'll talk a little bit about these confidence and prediction intervals, and I'll show you a little picture to kind of help illustrate the difference between them. And then a question here around a prediction interval for a single future observation versus a simultaneous prediction interval. So I'd like to get a sense for how many of you know about simultaneous prediction intervals. Okay, so it looks like a simultaneous prediction intervals are definitely not as commonly used as a prediction interval for a single future observation. So it looks like a large number of you are not familiar with that. So as we go through that portion, I'll make sure that we talk through that in more detail a little bit about simultaneous prediction intervals, and I'll provide a reference as well to get some more information beyond what we'll talk about today with that. So I believe, Ashley, was that the last question? Oh,
one more.
Actually, one more. Sorry, I forgot one more question here. So, based on what you know today, before we talk about this, what do you think would be a good number of confirmation runs to perform? Okay, so looking at that, looks like we've got a very common recommendation of a few, and that's something that I read quite often in the literature and looking in the literature. You know, they would say a few, and there wasn't really any necessarily justification for that. So what I'm going to hopefully show you today is some justification for what is a good number, and I'll kind of give you an answer at the end of this based on some of the results that we'll show here. So thank you everyone for taking the time to answer some of those questions. That's helpful for me as we kind of talk through this and understanding some of the background here. So let me go into the presentation. So Ashley, is the screen showing them?
Yes, I believe it is.
Okay. So before I get into this, I want to just share briefly a little bit of background that helps understand why I was interested in this topic. So W.L. Gore is a manufacturing company, and experiments are bread and butter. So over the last 10 years that I've been, about the 10 years that I've been at Gore, I've been doing many kinds of experiments in new product development and designing new products. One of our most famous products is the Gore-Tex fabric. But I've also been working in the medical products division, where we do many experiments in designing new medical devices, in designing manufacturing equipment, optimizing manufacturing equipment for building medical devices and Gore-Tex fabrics. And one of so DOE really is a bread and butter for a lot of the work that I've been doing over the last 10 years. So what I'm hoping to do today over the next 45 minutes is to kind of talk a little bit about a high-level DOE framework. For some of you, there may be pieces of this that will be familiar, and then maybe some pieces here that may be a little bit new. I'll talk a little bit about why I think confirmation really matters, why it's an important thing to do when you're doing experiments. I'll talk about some ways that you can assess confirmations. So I mentioned those intervals previously, so I'll talk a little bit about some of those intervals and how you can use those intervals to assess whether or not your confirmation runs are good, rather than having some sort of subjective, yeah, I think those confirmation runs were close enough to what we expected. I'll show some results, simulation studies that we did that will provide some justification for what is the best way to assess those confirmation runs, and also some sample size recommendations. And then I'll talk about some things that you can do if your confirmation fails. So if you do an experiment and then you do some follow-up confirmation runs and you find that there's a difference there, what does that mean? That's an important issue. And just to note, all of this is really based on my work over the last 10 years in doing many different types of experiments and many different types of scenarios. So, for more information, there is a paper that I wrote that is the same title, Confirmation Runs in Design of Experiments, that has, I just approved the proofs a couple of weeks ago, so that will be appearing shortly here in the Journal of Quality Technology in the April issue, so that should be coming out in the next month or so. I'm excited to see that paper appear in there, and this will have all more details beyond what we'll talk about today. So I would refer you to that paper when it appears for more information if you have lingering questions based on what we talked about today. Before, I'd like to give a nod to a couple of individuals that were influential. I didn't know either of these individuals personally. Both of them have passed on, but the person on the left is a man by the name of George Box. And George Box is relatively famous in the statistical world, and different statements that have been attributed to him, such as all models are wrong and some are useful and whatnot. But one of George Box's big ideas that he really taught and believed was this idea of sequential experimentation and discovery, this cycle in this learning process, that you do an experiment, you learn something from it, and then you do additional experiments and learn something from it, and not trying to do these great, big, huge experiments, but do a series of smaller experiments as the most effective way to get real insight and knowledge around the world around us. The one on the right is Søren Bisgaard, and Søren was a big advocate in the literature about different experiments have different purposes, and that there's not a one-size-fits-all type of experiment that you do, and that you really have to tailor the experiment to the problem that you're trying to solve. And as I was kind of doing this research and this learning, I found myself coming across multiple papers and writings that these two individuals had written, and so their thinking kind of influences what I'm going to share with you today. So here is a very high-level framework for DOE. I call these different phases or different steps that go in the process. There's a lot of literature out here that talks about the beginning part of this. If you go to any of these classical design of experiments, textbooks, things like that, they will talk about screening experiments. So things like factorial designs, fractional factorial designs, Placker-Berman designs, many other types of screening experiments that really try to address what are the most important factors. And then those screening experiments lead to some follow-up experiments, oftentimes a response surface type experiment, maybe a central composite design or a box-Venken design, maybe some optimal design. The goal there being to develop a model to describe the relationship between the factors of interest and some response. And as part of that model building, there's some optimization that happens. There's a lot of literature that covers that middle piece. There's a lot less that talks about that left-hand side of it, which is called range finding. And I find that that's an important step that's not necessarily talked about a lot, where you get a brand new piece of equipment, manufacturing equipment, or a brand new design, and you kind of have to just play around with that equipment. You have to play around with things a little bit. It's nothing formal, planned experiment, just trying to get what are the factor ranges that I'm going to use for the subsequent experiments. So I'm not going to talk a lot about that, but what I want to focus today is really this confirmation piece that I think is often mentioned passing in the literature, but I think is more important than what is mentioned. And here we're talking, I've got my model, I've optimized it, I've figured out where I want to run. Now I need to actually get data points at that spot to confirm that I get the result that I expect to get based off of the model. Is my prediction accurate? And in some cases, we want that confirmation to be a consistent or repeatable demonstration over time. And sometimes we have to demonstrate that in the actual environment, with all of the noise and variability that can happen in real processes, do I still get the results that I expect to get? So that's where our focus is today. What's not in scope today is when we're talking about computer experiments and physical experiments. There's a body of literature out there that talks about you have a computer model that maybe you have built to simulate something, and then you want to confirm the computer output with some physical results. And so there's a whole body of literature that addresses that. We're not talking about confirmation of hypotheses or significant factors. So sometimes when you get into literature, you'll hear people talk about confirmation when they're really talking more about test of significance. And, well, does the temperature affect my response? Does the time affect the response? And that's not what we're focusing on here. I already know what my significant factors are. I've got a model that describes the relationship between those significant factors. And then the last piece is I'm not going to talk about Taguchi arrays. When you look at the literature that talks about Taguchi experiments, confirmation is an important part of that. What I've found in those Taguchi experiments are two-level experiments and many factors, and there's not a model building step in those Taguchi experiments. So what may happen is you may have a large number of factors at two levels, and you run a number of different combinations, and then you kind of select use the signal-to-noise ratios to determine which factor combination will be the best for the future, and there's some confirmation there. So the Taguchi approach is good in recommending a confirmation approach, but there's no real model building as part of that. It kind of jumps from the screening to confirmation. And so I'm not going to talk about it in that context as well. So why does confirmation really matter? Well, one of the things that I've found is that oftentimes your experiments may be done in a lab or a pilot plant or a smaller scale piece of equipment compared to the actual production. And you want to, at the actual production, as much as you can try to mimic that, you can never completely mimic it in the lab. And so you want to make sure that whatever results that you get out of the lab work in production, and that you're getting the results that you expect in the actual environment with the actual equipment that you have. Another reason is regulatory requirements. So I work in a medical device industry, and we have regulatory requirements. So let's take as a simple example, if I have two factors, I call them X1 and X2, and I have low and high levels for each of them, along with a center point. And if I did that experiment as my model building, and I were to optimize, and suppose that based on that model, my optimum was in this red mark here, and the X marks the spot here. If that were my optimum, I don't actually have any data collected of that. Some of the regulatory bodies are going to want data at the X. So I need to actually run at that spot to demonstrate that the response or the output that I get at the X is acceptable. I can't just, the model's not enough. I actually have to gather data at that point. And then lastly, as many of us know, there's variation in all processes. And Myers, in a really nice paper a few years back, he kind of talked about this variation. And he said that one must always remember that optima are stochastic in nature. When we think of optimum, oftentimes we forget that optimums have variation. That the optimum is only a point based on a model. And so in reality, the true optimum may be a little bit different than the optimum that we calculated based on our model. And so therefore, it would be important for us to confirm to make sure that the optimum that we predicted really is the optimum. And that's where you need to do additional confirmatory experiments around that region of the optimum, in some cases, to making sure that you really got it. It may be a missed opportunity, and if you did not follow up that, as you may say, the model told me this was the optimum, and it may have been a little bit in a different direction from that, and I may have missed an opportunity to have an even better process than what I could have had. And then lastly here, there's increasing process complexity. So for example, in a generic process, you may have multiple steps in a manufacturing process before it leads to that final product. And some of those steps may be done in different locations, they may be done in different countries. The supply chain is getting more and more complex for many different processes, and it becomes challenging to do an experiment that covers all of those steps. So sometimes, and in addition, you may have too many factors to try to study all of the factors across all of the steps that may impact that final product. So you may do a DOE on a portion of that. So let's say I do a DOE that covers the factors in step 1 and step 2. Now I may be able to actually measure something about that product at the end of step 2, right? And I can try to optimize the factors within step 1 and step 2 to optimize the response that I can measure at the end of step 2, right? But I still want to confirm here in the final product, I still want to run, do some runs all the way through all the steps, get the final product, and make sure that my final output that the customer sees is acceptable. So when it talks about confirmation, what does the literature say? In doing this review of the literature, so Vining and Myers in a paper, they suggested, well, they should do at least one confirmation run. Right? They talk a little bit about doing a small experiment in the vicinity of that optimum. Anderson and Kraber, in another paper, they talk about using a prediction interval to compare the confirmation run. Notice confirmation run is singular in that case. The NIST handbook, this is a handbook of statistical methods that is freely available on the web. They talk about taking a minimum of 3 runs to be able to estimate the variability. They don't really describe why 3 or what you would do with the 3 after you calculate them. And then more recently, Simpson, in a paper in Quality Engineering, talked about taking a small number, 3 to 8, he called them validation runs. In our purposes, they're confirmation runs. And he talked about those points should fall within the limits of prediction intervals. And so that was kind of the closest or most detailed recommendation that I could find. And there are many others out there in the literature that just say a few or one with little elaboration on that. So that's what we're going to get to today. So first thing I want to talk about is how do I actually assess confirmation runs? So I found 3 approaches. The first 3 bullets that are listed here were 3 approaches that were recommended in the literature. And the last 3 are approaches that I'm going to propose or then suggest, and I'll show the simulation study a little bit later, that compared the different methods. Right? And these have to do with confidence intervals and prediction intervals, and confidence intervals on different things and prediction intervals on different things. Right? So I'm going to illustrate this with a picture to try to illustrate these 6 approaches. So let's take a simple case where I just have a single factor, 1 dimension, but recognize this concept still applies if you have multiple dimensions, multi-dimension response surface. Right? So let's say I have data that follow a quadratic relationship. So I could fit a model with quadratic terms to describe the relationship between the factor and the response. Right? I took some points, some data at different points, and then I collect say 3 confirmation runs. So those are the 3 stars there at the optimum. So the red line is your model, right? There's some variability around that model, and then there's some variability in the confirmation runs. Right? So our model says our optimum should be at 0.5, at the peak, if I'm trying to maximize the response in this example. Right? So what the first approach that's been recommended in the literature was to take a confidence interval on that regression line. So that's what that shaded band is representing. And this is these confidence intervals that I'm showing you here was done in JUMP statistical software. So I've got a band there. That confidence interval band is around the true mean response. It doesn't say anything about individual variability and whatnot. And so you'll see in this case that you get points that are outside of that confidence interval band. I'm going to show you a little later in the simulation that this approach doesn't work, but it has been recommended in the literature, but I do not recommend it as an approach because it doesn't account for the individual variability in the runs themselves. So you would take the band, and if any of those individual confirmation runs fell outside of the band, you would fail the confirmation. The second approach is going to be a little bit better in that rather than doing a confidence interval on the mean, I'm going to do a prediction interval for the next future observation. So in a regression context like I've got here, a prediction interval band is for an n of 1 for a single future observation. And so those bands are wider than what I showed you with the confidence interval approach. And so those prediction intervals should capture some of the individual variability. And you'll see in this case, most of the individuals do fall within those prediction interval bands. So the confirmation in this case will pass if each of those confirmation runs fall within the prediction interval band. The third approach that was recommended in the literature was to actually calculate a confidence interval on the confirmation runs themselves. So I'm not calculating any bands on the regression equation. So represented by the bars there is if I calculated a confidence interval using those 3 confirmation runs, and then I see if there's an overlap between that confidence interval and the red line, the model fit that I'm doing here. And if there was an overlap, then I would say that would be a failure of the confirmation. So those first 3 approaches are all approaches that have been recommended in the literature. The next 3 approaches I'm going to show you have not been suggested specifically in the literature. So the fourth approach here, actually when you do prediction intervals, you can do prediction intervals for a certain number of future samples. So many people are familiar with a prediction interval for a single future observation, but there are other types of prediction intervals out there. So in this case, you can do a prediction interval on a future mean of 3 observations. And that's what's represented by this solid line here. That would be the prediction interval. That would be the mean of the 3 confirmation runs, and then I compare the mean of the 3 confirmation runs to the prediction interval on the mean of 3 confirmation runs. And if that mean fell within the band, then I would say my confirmation has been successful. The last 2 approaches are similar, which are based on simultaneous prediction intervals. So when we say a simultaneous prediction interval, we're not just talking about the prediction interval on just the next future observations. So a prediction interval for the next future observation would say something like, I'm 99% confident that the next individual is between 4 and 7. But if I have a simultaneous prediction interval, then I say 99% confidence that all of the next 3 individuals are between the 2 numbers in the interval. So the simultaneous prediction intervals account for the fact that you have multiple future individuals that you were talking about, not just a single future individual. Now those simultaneous prediction intervals, it turns out they're not as easy to calculate. The exact formula is a little tricky, and so there are a couple of different ways that you can approximate them. So one way that I'm showing you here is to use a Bonferroni correction. So all that essentially means is that I take my confidence and I split it up by the number of confirmation runs that I'm doing. So for example, if I had a 99% prediction interval for one future observation, and I wanted to calculate a simultaneous prediction interval for 5 observations, I would take the 99%, subtract that from 1 to get the 1% left over, take that 1% divided by 5, the number of runs, and that would be equivalent to calculating a 99.8% prediction interval for one single future observation. And if I calculate that 99.8% for one future observation, that would be equivalent to a 99% simultaneous prediction interval for the next 5 future observations. So the math is not too difficult to do with that. If you can calculate a prediction interval for 1, you can calculate this approximation for prediction intervals for multiple. And it turns out that the approximation is quite accurate. So JUMP statistical software, which is one that I often use, actually uses this Bonferroni correction in calculating these simultaneous prediction intervals. There is a little more exact way to calculate that simultaneous prediction interval, which uses what's called the multivariate t-statistic. So you can't just use a standard t-statistic or a t-distribution. You have to use this multivariate t, and it's the distribution of the maximum of that. The math behind that is a little more complicated. I had to use SAS statistical software to actually calculate that to get these those intervals. So to kind of summarize here, the confidence interval on the mean will be the narrowest interval. The prediction interval on the mean will be a little wider. The prediction interval on a single future observation will be a little wider. And then the prediction intervals based on simultaneous intervals, whether I'm using the Bonferroni correction or the max multivariate t-statistic, those are going to be quite similar to that. So I kind of tried to show you here that each of these get a little bit successively wider for the situation. Now the one caveat that's not shown here is this confidence interval on the confirmation runs themselves. There's not really a band that was calculated as part of that. So hopefully that gives you a little bit of a sense of some of these different types of intervals. Like I say, if you want more information, the paper will describe it a little more. It has some of the formulas of how to do it. Another great book that also describes a lot of these differences in these intervals is a book by Hahn and Meeker. It's called Statistical Intervals, a Guide to Practitioners. It talks all about all different kinds of intervals for normal, non-normal data. It's a book that I've come back to many different times over the years and talking about these different intervals. I'm talking with Bill Meeker last year. I know there's a second edition that's in the works or pretty close to being released if it hasn't been released already. But even the original first edition has a lot of good information in it. So now I want to just talk a little bit, how do I assess whether or not these approaches are good? So what I did is I generated some data. I'm going to take kind of a simple case for illustration. So I take a quadratic model, something that can be handled with a central composite design. You have center points, axial points, and whatnot. And I calculated the intervals for all of those data sets, generated confirmation runs that come from the same distribution. So in other words, I don't want to see failures because these confirmation runs come from the same distribution as the actual original runs. So what I'm showing here is the probability of passing the confirmation. And in this case, I want a good number would be 0.95. That's why I've kind of drawn a line up there, 0.95, because I use 95% confidence for all of these intervals. Right? You'll see, for example, at the bottom dashed line, that's a confidence interval on the mean. What that's saying is if I use a large number of confirmation runs, say 5 to 10, I'm almost guaranteed to fail the confirmation. I'm almost guaranteed to get confirmation runs that fall outside of the confidence interval band. So that's telling me that approach is not a good approach. There's a thin solid line that's in the middle that corresponds to a prediction interval for 1 point. And maybe if I can show you a little bit here what I mean by that. Yeah, I won't be able to show you. I was trying to draw that or show that, but that's a prediction interval for an n of 1. This kind of solid line that drops down. So that starts off okay. It starts off around 95% if you have one run, but then as you increase the number of confirmation runs, that prediction interval for n of 1 doesn't work. And then you get up here on the top, the prediction interval on the mean and the simultaneous prediction intervals all kind of stay around that 0.95 or maybe a little above that 0.95, which is what we would want in this case. So what this shows to me is that all of the approaches that have been recommended in the literature don't work when you have multiple confirmation runs. And that you really need to use the right type of prediction interval that allows you to do multiple confirmation runs and correctly assess whether or not your confirmation failed or not. And I've done this type of simulation study for other types of situations and different types of experiments, different amounts of variability, and found similar conclusions across the board. That if you're going to do more than 1 or 2 confirmation runs and you want to evaluate it, you need to use prediction intervals on the mean or simultaneous prediction intervals. So then the next question that we asked was, well, how many should I do? Is 1 enough? Is a few enough? Do I need to do more? And so what I did is I took those good approaches from that first study that I just showed you, and I want to say, okay, what will happen if I use those approaches if there's a difference? So if the confirmation runs shift by some amount, will I be able to catch that using these methods? So the first thing I did in the study, first type of study, is I talked about a shift in the mean. So if the confirmation runs were significantly lower, shifted down from where you expect them to be in terms of the model, or if they shifted high, and then I would like my probability of passing the confirmation to be small, because that means, you know what, the confirmation run is different than the DOE run. Do I detect that? Do I catch that? So ideally, the probability of passing would be close to 0, which means that I'm failing when I'm supposed to. So here's just kind of a brief result here on the number of confirmation runs. And you'll see along the bottom axis is the delta just being the size of the shift. So if I'm at 0, then those things should all be close to 95%. And then as I increase my delta, as the confirmation runs get more and more different, I would like that value to get closer to 0. So you'll see in this case, the prediction interval on the mean, right, does quite well in detecting those mean shifts. The simultaneous prediction intervals can do all right if you have enough confirmation run. And one of the things that I noticed here is that the picture between the panel at 10 and the panel at 30 doesn't change a whole lot, regardless of the different method that you're talking about there. And there's not a huge difference between 5 and 10 either as well. So in terms of mean shifts, once you get into that 5, 10, and beyond that, you'll be able to detect them fairly well. And the last piece that I did on the simulation study was to not just do a mean shift, but talk about changes in variability. So in this case, you can have increases in variability, which is probably what we would care about if your actual process was more variable than what you had in your lab, or your DOE results, if it were more variable, you need to account for that somehow in the analysis. So we want to say, do the confirmation runs signal the changes in the variability? So we simulated the data, increasing amounts of variability, and one of the things that we added to this for reference or for comparison was a Brown-Forsyth test. A Brown-Forsyth test is just a test of equal variances. It's a variation on a Levene's test or an F test for variances. There are many different types of tests of equal variances out there. The Brown-Forsyth tends to be kind of a robust one. So I want to put that in there to show as a comparison in here. And so this is the simulation study results here, and you'll see that the bottom line is the Brown-Forsyth test, the test of equal variances, that is the best way to detect changes in variability, which isn't too much of a surprise compared to an interval method. But nonetheless, as your number of confirmation runs increases, the simultaneous prediction intervals actually can do quite well in detecting changes in variability once you increase the number of confirmation runs up to that 5, 10 plus range. So kind of the conclusions from the study is that you should increase the number of confirmation runs and use the right criteria for assessing them. If you increase the confirmation runs and use a prediction interval for a single future observation, you're going to fail, almost guaranteed. Right? Increasing the number of confirmation runs makes it easier to detect the differences that could be in there. You are going to need more data to detect differences in variability than you would in a mean. That isn't too surprising. And then lastly here, the more accurate your model is, the more effective the confirmation runs will be. So if I put more center points, if I do replicates, and I get a really good model, then it's easier to detect changes from that model. So those are kind of the conclusions from that. And again, as I mentioned in the paper, you can see more details within, see different scenarios and simulation results associated with them. So my recommendation based on this result is that 5 to 10 seems to be an appropriate minimum number. If you want to detect changes in variability, you're going to have to go larger than that. This 5 to 10 is larger than what has been recommended by the literature. So I'm recommending a larger number. The other thing that is not necessarily accounted for here is that in some cases when we do a confirmation, we want to demonstrate long-term, consistent, repeatable results. We want to be able to calculate a CPK on the data done at the confirmation runs, or we need to demonstrate a larger sample size for regulatory purposes or to demonstrate capability. Then in that case, you could look for sample size recommendations for calculating the CPK or to demonstrate long-term consistency, which is going to put you more into that 30 or 30 plus to really demonstrate long-term capability of a process. So hopefully that's kind of the answer that I got based on these results, which is larger than what has been recommended typically by the literature. So the last piece I'd like to talk about here is really what do I do if the confirmation fails? So when it fails, that indicates that there is some discrepancy between the original runs and the confirmation runs. And it may be that you've used the wrong criteria. Maybe you're using a confidence interval when you shouldn't be. Perhaps that is because the confirmation runs were not performed the same way, which may not be as much of a surprise. If you have a pilot plant in actual production, things are going to be different. You're trying to get that similarity as much as possible, but sometimes we can't mimic that completely, but that may explain that discrepancy. Perhaps your model is inadequate. Perhaps there's something else going on in there with that model that you need to do some further model building experiments to refine that model to capture something that you didn't capture initially. And lastly, perhaps the variability is larger or the variability is non-constant. In some cases, we may expect that variability to be larger in the lab versus the production. So we wouldn't be surprised necessarily if the confirmation runs exhibited more variability than the original. And then lastly, there may be some noise factors in the confirmation experiment that were not in the original, and that may be the root cause for the variability differences between the two. But this failure really is an opportunity to gain more process understanding, refine models, get better models to explain what's really going on in the processes. So this really shouldn't be, it's not all bad news if the confirmation fails. So some open questions that we really have here that have not been, some open questions that have not been really addressed in the literature is what do you do when you are trying to confirm a region or maybe multiple points? The simulation results that I've shared with you is really focused around a single optimum. But sometimes you want to find an optimum region. You say, you know what, for manufacturing reasons, I'd really like to be able to run anywhere within a 5-degree window, for example. And so how can I confirm an entire range or window settings? I've not looked at more complicated types of experiments, say mixture experiments, for example, split plots, blocking, and whatnot, and how conformation would work there. My guess is that a lot of the same conclusions would probably be similar across there. That you could think about simultaneous prediction intervals would probably be a good approach for other types of designs. For other types of designs, the calculation of those prediction intervals is a little more complex, so that will make it a little more challenging. And then lastly, I've focused on an interval approach, but there may be other approaches out there that are non-interval approaches for assessing confirmation. So to summarize what we've talked about today, the literature doesn't give a lot of guidance. There are many common assessment approaches out there that don't work really well. From my perspective, a simultaneous prediction interval seems to be kind of the best overall approach. And if you're using the Bonferroni correction, it's something that you can do relatively easy as long as you know how to do a prediction interval for a single future observation. 5 to 10 confirmation runs seems to be an appropriate number. And then lastly, there's a lot of reasons why a confirmation might fail, which may not necessarily be a bad thing. So here's some of the references that I have referred to in this paper. In this presentation, the end of the paper has a full list of many different types of things that have been done out there. So I'm going to turn it back over to Ashley for a couple of last poll questions. So don't go away just yet.
Thanks, Willis. I will cut to the poll questions in just a second. We did have a couple questions come in, Willis, as you were speaking. Okay. One of the questions referred to your first simulation after you introduced your first simulation study, and it asked, did you use the true model or the fitted model? In applications, we will only have the fitted model only, which will add another source of error.
Yeah, I'm having a hard time hearing you there, Ashley. Sorry about that. Just try that one more time.
I apologize. Can you hear me now?
Yeah.
Okay. In your simulation, did you use the true model or the fitted model? In application, we will only have the fitted model. If we can't get to that in time, I can send out the email afterwards.
Okay. Yeah, sorry about that, Mr. Nutt.
Oh, that's fine. So I will cut to the poll questions to end us out today. The first one, we are curious if you learned something today. Okay, thanks for your response for that one. And lastly, are you more likely now to do confirmation runs in the future? Okay, that was an excellent presentation. Thank you, Willis. We're going to end in a couple minutes, but a recording of the webinar will be available within a few days on the division's YouTube channel at youtube.com/ASQ Please be sure to share this webinar and our archived webinars with your friends, coworkers, and colleagues. We encourage you to check out the division's LinkedIn page as well as our events calendar, which can be viewed at asq.org/statistics for the latest news on webinars, conferences, and many other topics. That's all the time we have today. Thanks everyone for joining us, and thank you again, Willis, for presenting with the statistics division. Hope everyone has a wonderful weekend.